This example is the field of a solenoid. A solenoid consists of a helical winding of wire around the surface of a cylindrical form. Ordinarily, the turns are so closely spaced that each one is very nearly a circular loop. There may be several layers of windings. For simplicity, we have shown a solenoid here as having only a few turns. All turns carry the same current I, and the total magnetic field vector B at every point is the vector sum of the fields caused by the individual turns. The figure shows field lines in the XY and YZ planes. Exact calculations show that for a long, closely wound solenoid, half the lines passing through a cross section at the centre emerge from the ends and half leak out through the windings between centre and end. If the length of the solenoid is large compared with its cross-sectional diameter, the internal field near its centre is very nearly uniform and parallel to the axis, and the external field near the centre is very small. The internal field at or near the centre can then be found by use of Ampere's law. We chose as our integration path the broken line rectangle, so we're going to use this A, B, C, D. And here's our solenoid here. Here are the windings here, so you can see all the windings. And these are the magnetic field lines going through. So you can see that in the middle they're more or less uniform. And in fact, if this is long enough and the windings are close enough, if the diameter is very small and this is long enough, then you can see in the middle are virtually uniform. So we're going to integrate now in this area here. So side AB of length L is parallel. You can see that that's parallel to the axis of the solenoid. Sides BC and DA are taken to be very long, so we're going to assume that these are very, very long distances, these two here. So that side CD, so this side here, is far from the solenoid, and the field at this side is negligibly small. By symmetry, the magnetic field alongside AB is parallel and is constant. So for this side, the parallel component of the B field equals B. So you can see that we can just use that the integral of B dot dl is simply BL. So what we're going to do then is let N be the number of turns per unit length. So we're going to introduce N. We're going to say that N is the number of turns per unit length in the windings. If we count out the number of turns along L, we're going to get NL. That will give us the total number of turns along L. Yeah. Each of these turns passes once through the rectangle ABCD and carries a current I, where I is the current in the windings. The total current through the rectangle is going to be NLI, and from Ampere's law we know that BL, cancel out the L's here, divide through by L, and you just end up with B mu naught N, which is the number of turns per unit length, times I. So that's it. So now when you've got a solenoid and you know how many turns it is and the current going through, then you can work out the magnetic field vector B.